Okay, so here is my second attempt to make this video with some audio. Hopefully it works. So basic idea of what we have so far is we are doing um, scalar surface integrals, and we're going to do them on surfaces that are explicitly defined. So we're going to look at that. And there's really a nice kind of way to do these because the normal vector, when you're explicitly defined surface, is negative zx, negative zy1, which means the magnitude is the square root of zx squared, zy squared plus 1, and sum of them. And so that gives us a nice formula. And so there's this theorem that if you evaluate a surface integral on a scalar valued function for explicitly defined first surface, it means z equals gxy for some xy in some region R, then the surface integral, instead of having to parameterize this the surface S and then plugging that in, you can just plug in this surface in for the z component into your function, and then multiply by the fudge factor, which in this case tx cross ty is that. And the reason is because if you do a parameterization where x is x, y is y, and z is gxy, and you take the tangent vectors, you get 1, 0, g sub x, 0, 1, g sub y, and then taking their cross product, you get negative gx, negative gy, 1. And so that's kind of where it comes from. And so let's use that theorem real quick to evaluate a particular surface integral. So here, this is just a standard scalar valued surface integral. It has a scalar function e to the z here, s ds, and they tell us the surface S is x plus y plus z equals 1 in the first octant. And so the reason I know that this is going to be good to use the explicit formula on is because this is a plane, so that's drawn right here. And so we can solve for z really easily and then get an explicit formula for z as a function of x and y, and then plug it into this formula. That's the kind of idea. So let's first solve for z. So you get z equals 1 minus x minus y. And then I should also look at the projection in the xy plane, because that's going to be the region R we're going to integrate over. And so that will just be a little triangle like that, where that's 1, and this line is just 1 minus x minus y equals 0, or y equals 1 minus x. And so that will be our region R that we're going to integrate over. And so this double integral over s e to the z ds, what it becomes is, well, I guess we need to do a couple more things. I need to compute this fudge factor, which is kind of changing the ds to the dA, where the dA is now that area R that we're going to integrate over. It's like what is changing when we do on the surface, and that's what this integral will tell us. So I need to compute those things. So I need z sub x. Z sub x will just be, if I take the integral of this thing with respect to x, I just get negative 1. Z sub y is also negative 1. So therefore, this squared of z sub x squared plus z sub y squared plus 1, that just equals square root of 1 plus 1 plus 1, which is root 3. So this is going to equal root 3. Maybe I shouldn't. I'll pull it out later. So it's going to be equal to integral, and I'm integrating now over, over the xy region. And so I can slice this up however I want. So if I do dx slices on the outside, 0, 1, and then dy slices will go from 0 to 1 minus x, because that's what y equals. And then it's e, and then I have to plug in the function. So it's e to the 1 minus x minus y, and then it's dy, and then the fudge factor, the fudge factor, which is root 3, and then dy dx. And so this, if you can set that integral up, that's a majority of the fight. And then actually doing the integral now, this is just a standard double integral. And so I'll do it really quick, but I think it becomes negative e to the 1 minus x minus y evaluated from, what is that, 0 to 1 minus x, and then the integral from 0 to 1, and then the root 3 on the outside dx. If you plug in 1 minus x, you get minus, it's a 0 by the way, you get e to the 0 plus e to the 1 minus x, because of the two minus signs. And then I'm going to integrate that from 0 to 1 dx, root 3. If I do that again, I get negative x minus e to the 1 minus x evaluated from 0 to 1 times root 3. And so I get root 3 times negative 1 minus e to the 0. That's the first part. And then minus, if I plug in 0, I get 0 minus e to the 1. And so that's some number. We'll just leave it like that. And so kind of in general, so the kind of general thing is that if you have an explicitly, I think there's no I there, explicitly defined surface, meaning z equals some g, so z equals g of xy, then the fudge factor for that guy, the fudge factor is the square root of take the partial with respect to x squared plus the partial with respect to y squared plus 1. And so that's going to be kind of how we'll do it for the explicitly defined ones. And then let me just do one last thing where I introduce the surface flux integrals. And then in the next video, I'll do the example. So just a reminder from before, if you have some enclosed kind of loop or curve, and you have some vector field that's acting in the plane, we can kind of ask, how does that vector field go through that curve? Meaning, how does it perpendicularly go through it? And that's what's called a flux integral. And so the idea is that we're going to take that up a dimension. And so now we're going to do it for a surface. And so our surfaces are going to be closed surfaces, meaning that they enclose a region. So there's kind of like no gaps or holes and no boundary. So we're going to do I think, do surfaces without boundary. Although I guess for Stokes' theorem, we're going to do surfaces that have boundaries. But anyways, they just need to enclose some region. And we have to define, and we have a vector field, which is going to have 3 components now. So it has an f, g, and an h. So that's the x component of the vector field, the y component, and the z component, which are just functions of x, y, and z. So it's a bunch of arrows in 3-dimensional space, and you have some surface. And then the surface itself comes equipped with a normal vector. So a vector that points normal to the surface. So meaning it makes a 90-degree angle with it. And then the question we can ask is, if you have a vector field and some surface, and I guess we should also mention that there's 2 types of normal vectors. There's the outward-facing normal and then the inward-facing normal. There's 2. And so we have to define the outside of our surface and then the inside. And so if you think about like a surface of a sphere, the outside is the outside of the sphere and the inside would be on the inside of the sphere. And so that's the kind of idea. And so when we're talking about surface integral, flux integral, we're going to talk about how is it doing with the unit normal that's facing out in the outward direction. So that's our outward facing normal. And so the vector field could be at every point, could be pointing in some direction, and then you can kind of take their cosine and their dot product, and that will tell you how much it is in the same direction. If it's completely in the same direction, then their dot product will just be the magnitude of f. And if it's in the opposite direction, you'll get a negative. And if it's perpendicular to the unit normal, meaning it goes in the direction of the surface, then you get no flux. And so the idea is a surface flux integral is adding up all these kind of dot products of your vector field with your surface. And so what it represents kind of physically is the total flux of the surface. We're computing this dot product at every point on the surface and saying how much of my vector field is escaping through my surface and going through. And so how we compute it is we have to use parameterization. And so the way we do that with a parameterized surface is, so you have some vector field f, g, and h. You have some parameterized surface r of u and v. R is going to be a region in the UV plane. Then the way you compute this is you plug in the parameterization into f, and we turn the normal vector, which is just the cross product of the 2 tangent vectors divided by its magnitude. But then a beautiful thing happens because we can, when we change ds to dA, it actually cancels out, and you just get the normal vector, which comes from the cross product, and you just dot those 2 things. And so this will become a scalar, and then it becomes a regular scalar integral at that point, or double integral. There's a nice version if it's an explicitly defined function. So if you have an explicitly defined function z equals g of xy, then the normal vector, as we said before, is negative z sub x and negative z sub y 1, which is just the partial of that thing with respect to x and partial with respect to y. That's our normal vector. And so we get to dot that vector with this vector field, and you get this. The only thing that you need to make sure of here is that f, g, and h are only in terms of x and y here, because we're going to do dA over some region. And so I'll do a couple of examples, especially when we do Stokes' theorem. I'll show an example of this. And so this one will be really, really helpful for us, actually. So that should get you going. Sorry that the first video didn't work, but hopefully this one does. All right, take care.